47 NASA 1. Go ahead. We've got loads set on the red phone here, and we're ready for step Bravo.
Welcome to the mission brief for Flight 168.
We'll taxi into position at runway 25. We'll go out and make the right downwind departure towards Daggett, Viewer.
Going to be taking off almost on the hour. It's 2 minutes prior, and you're going to be making a right-hand turn, proceeding to your first science point.
What we're looking at is a galaxy which is known to have a supermassive black hole at its center. What we need to do is to point the telescope at 45 degrees elevation.
If we see it, this will only be, I think, the third time a supernova like this has ever been seen in the mid-infrared. So.
The doors have been all armed. Everyone has been trained on how to open them. As you push the door, make sure you let it go, or you will exit a lot quicker than you wanted to.
Radio system here. Southwest 510, contact open center 121.25. 12125, South 510. Have a good night. How's the positioning, Ted? It's a little bit. It looks fine, Ellen. We're real high.
I was born in the generation where the Apollo astronauts started to walk on the moon. And that got me very excited about wanting to be an astronaut myself. I think a lot of kids really wanted to be an astronaut when they were younger.
I grew up with the space shuttle program. One of my dreams as a kid was to become an astronaut.
From 6th grade when I went to space camp for the first time, kind of always had this dream of something with NASA.
When I was young, I always dreamed about being an astronaut, getting into space. I'm just so excited that NASA has given me this opportunity to participate in this program.
Now I have an actual chance to fly on SOFIA.
This is fulfilling that one of my lifelong dreams.
This gives me my chance to actually be part of a NASA mission.
Now, Pamela, are these nodding and chopping things normal function?
Yes, nod, chop, and dither. Chop is a secondary mirror, nod is the primary mirror, dither has to do with the light coming down the bore sight to the instrument, and they'll move it around so where there's a bad pixel or channel, you don't have a hole in your data.
We have two cameras. One operates from 5 to 25 microns, the other from 25 to 40 microns. And with a dichroic beam splitter, you can image in both wavelengths at once.
I like supernovae in particular because everything that we're made of, all the atoms that you see around us, all that was made inside of a star. The universe would be a boring place without stars. So supernovae are actually responsible for everything that's interesting in the universe, including planets and people and things like that. The way these supernovae happen is these are very massive stars, much more massive than the sun. Massive stars just tend to be very violent, very short-lived. They throw off a lot of material, and then the shock wave from the supernova goes out and runs into that and heats all that material up to where we can see it again. We had detected this with another telescope called Spitzer, which is a space telescope, but Spitzer doesn't go out as far in wavelength as SOFIA. So that's kind of what we're trying to do here, is get this longer wavelength observation. It looks just like a star if we end up seeing anything. They didn't see anything last night either.
The scientist who is investigating the supernova, they've actually haven't found any data. This is an important part of science that I'm going to bring back to the students, is that sometimes hypotheses are not supported, and this is just as important as if they were supported.
We can turn all of these things into teachable moments in our classroom, teaching about measurements and conversions and units, and then real-life application of the engineered design process. How in the world is this plane even up in the air with the side of it open?
The telescope is actually run by some gyroscopes. The gyroscopes actually help to keep the pointing of the telescope aimed at the right spot. I have a little demonstration here I'd like to show with a toy gyroscope and my toy airplane. By the law of conservation of angular momentum, when the telescope moves one way, the gyroscope is going to move the other way to keep everything in balance. There we go. So now we've got it, and I'm going to be jiggling the airplane a little bit to keep it on the board. And this motion is very similar to the motion of the telescope in trying to maintain pointing as the airplane is moving. This is a magnetometer in a bottle, and it's a real simple device. Anybody can build it. It's basically inside the bottle I have a mirror, and I have a magnet hooked onto that mirror, and it's hanging by a string. Over here on this side, I have a laser pointer, and that laser pointer is pointing right at that mirror, and it's reflecting over to the card on the back here where we have it scaled. And so as we travel through the various latitudes and longitudes of the Earth's magnetic field while we're on the airplane, this is going to move back and forth. This is important to SOFIA because a lot of the instruments are very sensitive with the Earth's magnetic field. So is the prism, it splits the light and then it diffracts it. So does it actually take and make a finer set of spectra?
The prism itself will produce the dispersion. What the grating does is it selects the order of how that dispersion falls on the detector. The advantage of a grism is the grism, you can use a smaller optical component and get the same dispersion. And we can put those grisms right in the filter wheels. Basically, it allows you to switch back and forth between imaging and spectroscopy on the fly.
And talking to the astronomers and astrophysicists here tonight provided great background and great context for when I integrate a lot of the engineering challenges that go along with SOFIA into my curriculum.
So there's this ring of dust and gas about 3 light years in radius around the central cluster, that supermassive black hole. If you look more closely, you'll see that there's these dark bands at some fixed distance away from that central cluster. These are some of the contours from what we took from forecasts. So this is at 37 microns, and you can see that the contours line up pretty well with where those dark bands are located. There's no other observatory that's capable of looking at 37 microns. But SOFIA is the only observatory capable of getting this information right now.
This is very exciting to see the actual data being taken and then eventually being able to be used in research papers and research.
We've looked at supernova, we've looked at a donut ring around the galaxy. We're looking at other objects in the sky, big red giant, and the disks around it. And all of these are parts of astronomy. And astronomy is really amazing because if you look at it in the infrared light, you're going to see it differently than when you look at it in the visible light.
We'll be able to take some of the content we've learned here and teach incoming 7th, 8th, and 9th graders at Air Camp USA all about infrared spectrum, different aspects to the engineer design process with AFRL at Wright Pat in Dayton, Ohio, and then also be able to show other applications of mapping flight plans, the integration of the total systems.
One of the things that I always thought was just incredible was the idea of just exploration for the sake of exploration and to learn more about our origins or possibly where we're going. If my students were here tonight, I would say that this SOFIA mission proves that there is a purpose to learning. There are so many applications of math, science, and engineering that are being demonstrated here this evening that there are practical applications for themes that you wouldn't ordinarily think that you would use. So it's kind of nice that I can use this as a reference point when my students say, Mr. Jenkins, why are we learning this? And I can give them a specific example, and I could even tell them some of the wonderful people that we've worked with tonight to accomplish this wonderful exploration.
The kids have sent me a lot of emails and they're just really anxious for me to get back and tell them all about this opportunity. I would definitely want to share to them all the different people that are involved in getting this flight off the ground. I think it's amazing how many paths people take to come to work at NASA, and how there's so many different jobs and how well coordinated it is to get this aircraft off the ground and to get this science running and to get the telescope running and to collect the data and everything that's involved, so that they realize that this is not just a one-man operation, that NASA is a lot of different people with a lot of different backgrounds coming together and getting this science done.